Okay, so welcome again to the second part of this seminar. So we had a senior fellow giving a first talk, and then the junior fellow will give a talk now. And it's a real pleasure to introduce Yailen Martinez to you. Yailen came to the VUB to do a master in computer science. So she graduated from that master program in 2008. And then the two best students of that year received a scholarship to continue doing a PhD. And that was, so Yailen was one of these students. And then she did a PhD with me. And so therefore, I'm very happy, of course, to introduce her to you. And she will be talking, amongst other things, about what she has been doing in her PhD, and also after, well, returning to Cuba. I must say that Yailen is actually from Cuba, so you did your bachelor there, and we have a lot of collaboration with Cuba, actually with UCLV in particular, because it's a preferred partner of the VUB. And so after going back for a while to Cuba, you joined the lab. And actually it turns out that the work is still very relevant, and you have been collaborating on this idea also with Flanders Make, but maybe you will talk a bit about this. So I'm very happy to see that the ideas are being continued, and I will let you explain. And I will already apologize that at some moment I will need to disappear, go back to the lab, because students still have exams, so I have to be there on time to do some oral exams. But Yailen, yeah, you have the mic. Yeah.
Okay. Thank you, Anne, for the introduction, and well, also thank BrIAS for the opportunity of presenting this work here. As Anne already mentioned, I will briefly give a general idea of the very basic approach that we started with my PhD and how it has been adapted so it could be applied for two different scenarios with Flanders Make. So in general, scheduling problems, I mean, we can say that scheduling is a decision-making process that it can be found in many scenarios in our daily life. It can be as easy as you preparing your plan for the day. You have a set of tasks that you have to execute, and in order to do that, you have an objective in mind. So it might be that you have a due date, you have a deadline, or you can also say that you just want to finish all your tasks as soon as possible so you can go home early. So you prepare a plan, having an objective in mind, and typical dispatching rules, as they are called, really common one and really widely used are first in, first out, or shortest processing time. You might want to execute the task you will finish the fastest, or the earliest due date, so maybe you want to give priority to the one that you are supposed to finish by a specific due date. But then once the tasks start to repeat, so if you have to repeat a specific number of tasks during several days, during the week or the month, then we can say that you can start learning from experience. So every time you're repeating tasks, you start thinking, what can I do in a different way? It can be as easy as that, or it can go all the way to different scheduling problems, typical and well-researched scheduling problems that we can find in different scenarios. So for example, you can have timetabling, or we can have the nurse rostering or the nurse scheduling problems. We also have project scheduling, so typically you need to define what needs to be done, who is going to do it, and when exactly this needs to be done. And we are going to be focusing a bit more on production scheduling, so I will give a general idea. So for production scheduling, we can say that as a general characteristics, we always need to have jobs that are composed by operations, so tasks that need to be executed in a specific amount of resources for a specific amount of time. So we have basically what we can see here. So we have an operation that needs to have some specific processing time, and for this operation you might have a start date and a due date. Okay, so it's not mandatory, but you could have also this information. So we typically have different, in the operation research library, we have plenty of benchmarks or problem instances that we can solve from the many different types of scheduling problems we can find. So typically we receive a table, and this kind of table of the different jobs composed by different operations, this needs to be translated as a Gantt chart, which is a typical way to formalize or to visualize how is this the solution for this scheduling problem being constructed. So how we translate this table to this solution is something that we have to do by using a specific method, but we also need to take into account that all the things that you have to the right can also be present. So there could be, for example, setup times. So typical example is not the same to prepare dark chocolate after white chocolate, that's the other way around. So that could be some time in order to prepare the machines for the next task. You could also have order sequencing. So for example here, this job 1 is being composed by 3 operations. They need to be executed in a particular order. So you can have constraints for the ordering or not. That's also a possibility. You could have operation alternatives. So here we are just saying that you need to execute those 3 operations in order, but you could have alternatives. So this operation can be executed in this machine for this amount of time, or in the other one for this other amount of time. So there's an extra decision over there. You can have machine breakdowns. There could be some delays. And for all these things, we need to be prepared as the best we can. So in the manufacturing scheduling scenario, we can have different types of problems and different objective functions as well. So if we are talking about only one stage, if we have only one machine, then we can say we are talking about a single machine scheduling problem. If, on the other hand, we have parallel machines, then this is the parallel machine scheduling problem. And when this type of scenario gets a bit more complicated and you have multiple stages, then we have to take into account what are we doing here. So if we have jobs to execute, if you only build tables or chairs, and you always do it in the same way, so the jobs are always being executed in the same order, then we are talking about the flow chop scheduling problem. If you build, for example, chairs and tables, and each of them has its particular ordering, then we are saying that we are in the presence of a job chop scheduling problem. And if there is no ordering at all, then it's an open chop. These basic definitions can be a bit complicated in the case that we have multiple machines per stage. So if there is an extra decision, so if there can be alternative paths, then we are saying that in the same order for the flow shop, the alternative will be the hybrid flow shop. For the job shop, the alternative will be the flexible job shop. And for the open shop is the flexible open shop. So this terminology, we are going to be explaining it a bit just for the ones in green, so for the job shop and the flexible job shop scenario. Typical objective functions that we can find here when we are working in manufacturing scheduling is to minimize what is called the makespan, so that's the completion time for all the tasks. You could also want to minimize the average flow time, so the time the jobs spend in the system, or the average number of jobs in the system. And if we can also work with deadlines or with due dates, then we can also have, or we could also want to minimize the average tardiness, or minimize the maximum tardiness, or the number of tardy jobs that you have in the system. So typical approaches in order to solve scheduling problems can be exact methods. So we can have mixed integer linear programming, constraint programming, branch and bound, but we have to keep in mind that when the complexity of the problems start to increase, if you have a high number of jobs, a high number of machines, then, for example, a simple 10 jobs and 10 machine instance can take from minutes to hours to execute. So this computational time can also increase, and then we also need to take into account uncertainties, changes in general, unexpected events that can occur, not only machine breakdowns, but specific delays and so on. And all this information has to be taken into account at the same time than also solving the problem. And this kind of uncertainties sometimes are a bit more difficult to model in this kind of methods. So that's why when we search in literature, almost all the scheduling problems are also being solved by using heuristics or meta-heuristics based on sequencing or dispatching rules. For example, there have been results by using taboo search and colony optimization, genetic algorithms, and so on. And the first application of reinforcement learning in scheduling, we can say, was around the 90s. Then from here, it's possible to see that scheduling problems, they suggest natural formulation as distributed decision-making tasks. And of course, this character of being naturally distributed, it makes the idea that multi-agent systems may be exploited in a purposive way. We were, at that point, starting, let's say, the journey in reinforcement learning. We started collaborating with Anne, and then we said, okay, let's try. We were doing some experiments with different meta-heuristics for these kind of problems, and then we decided to start the journey in applying reinforcement learning for this kind of combinatorial optimization problem, and that's why our objective was to come up with some sort of generic multi-agent reinforcement learning approach for scheduling problems, one that is able to find solutions that are good enough. I mean, we want to have solutions in a reasonable amount of time, that these solutions are near optimal. If they are the optimal, the better, but of course, we are not talking about an exact method. And then, with the same basic approach, we could adapt it in order to satisfy the constraints of the corresponding scheduling problem, so that it could be adapted to different scenarios. And at the end, we also wanted to make solutions more robust by strategically introducing slack times, and I will also mention how this could be done. So briefly, I will be just explaining how we can define this multi-agent reinforcement learning perspective for scheduling problems. We will explain how it could be used for these two scenarios. We will also talk about robustness and criticality, which is an approach that was proposed in my PhD, and we will explain just how to adapt it in order to work with these two scenarios. One we call the kitting case, and also for the light switches scenario. So for reinforcement learning, as the previous speaker was saying, and I won't go into details because most of us already know a lot about it, but we can say that at the end, we want to map situations to actions in order to maximize a numerical reward signal, and at the end, we are going to have agents placed in a specific environment. At each time step, we are going to check what the environment is. We will receive a feedback signal from this environment, and by trial and error, and by interacting with this environment, we are going to learn how to solve this scheduling problem. And in our case, we are going to be using the Q-learning algorithm. So at the end, it's a model-free of-policy algorithm that can help us to find the optimal action selection policy. And what needs to be defined then here is by using this algorithm, how we could define what state and action, and which is the kind of reward or feedback we are going to give into the agents so they learn how to solve a particular scheduling problem. So at the end, of course, by talking about complex scenarios in the scheduling environment, we will be using multiple agents acting in this same environment. They could have common or individual reward, and I will also talk a bit about that. And of course, we do this because of the advantages of having an adaptive, scalable, and intuitive approach, and of course, due to the ability to solve problems that are too large for a centralized agent to solve. So, in order to apply these ideas for scheduling, when I was doing the PhD, we started checking what has been done and how we can establish something that could be used for the really, let's say, different types of scheduling problems, but can also have better results, and through an, let's say, a user-friendly interface can also help the user to communicate with the system and establish which are the preferences that need to be taken into account. And at that time, we found two ways of modeling. In this case, as I mentioned before, I will be talking about the job shop scheduling problem. So we have operations that need to be executed in different resources, and each job has precedence constraints that need to be taken into account. There were two alternatives at that time. So we could interpret it as a single Markov decision process, or we can interpret it as a multi-agent Markov decision process. So we can have like the general, let's say, a centralized point of view by representing the state of the system by the situation of all the resources as well as the processing status of all the jobs, or we can have an agent associated to each of the resources that you have in your system, and this agent will locally decide on elementary actions. Then at the end, we could have a joint action space by being composed by the actions that all the agents can take into account. And at the moment, the authors of this paper were proposing to use, of course, in this case, we are talking about minimizing the time it takes to execute all the tasks. They were using, with the learning algorithm, a cost function that was related or was given by the number of jobs that were in the queue of the system at that specific moment in time. So they were claiming that high costs are incurred when many jobs are waiting for further processing in the system, so we could say that the overall utilization of the resources is poor. So we took this idea, so at the end, we will have as many agents as resources we have in the system. The set of actions is going to give us the state of the agent at that specific moment in time. The action, so for the agent to select an action, it will be to take or to select an operation. So remember, the agents are placed in the resources. So at a specific moment in time, I know which are all the operations that are waiting in the queue for in order to be processed by that specific resource. So an action is to select one operation, and then the feedback signals we try with different ones. So we were also using a feedback signal related to the processing time or the solution quality, and we also use one that was a bit more related to the time it will take to process the jobs that are in the queue of the system. Because at some point, there could be two agents, for example, that they both have two elements in the queue, but it's not the same having two with a lower processing time than having two with a specifically higher processing time. And then as objective functions, here for the job shop scheduling problem, we were also mainly working with makespan because we didn't have due dates, but there were other scenarios where due dates were also included, so we were also able to test the algorithm by using tardiness as an objective. So basically, just to give you an example, this is something that this is more or less the idea of how are the instances of the operation research library being composed. So you basically receive a table like this. The first one is the description line stating the number of jobs and the number of resources, and then you have one line per job indicating the operation, where it needs to be executed, and how long it will take. So basically, the last line can be translated in job 5 must be processed first in machine 1 for 3 time steps. Then it has to go to machine 3 for 3 time steps, then to machine 5 for 9 time steps, and so on. So the idea of our algorithm is to take all this information, and then in order to start working, we have precedence constraints. We cannot process operation 1 before operation 0. So we basically have to take the first column, and we find out which are the resources that can immediately start working. So we just launch the first operation of each job. It will go to the queue of the resource that needs to process it, and then for all the resources that can actually execute something now, then all of them will take an action, and then after that, that's how the process is being executed. Once I take an action, then after finishing the processing of that operation, then I can release the next operation of that job, and that's basically what we do here. So assuming that for this agent, we are taking the second operation, and for the second agent, we are taking the first one. We are saying that, for example, in that case, job 3 operation 0 is already executed, so we can release the first operation of job 3, which in this case needs to go to machine 0. And that's how the process is being executed. So every time you are checking which are the resources that can actually perform an action, and then we are just saying, okay, just select one, and then based on that, we were using different feedback signals in different experiments, and I already mentioned them in the previous slide. So as feedback signal, we were using the same that the previous authors were proposing, so the number of jobs that are in the queues of the system, but we also took into account the sum of the processing times of those jobs that are still in the queue, and also we were also giving feedback based on the processing time of the actual operation. We also try with the global reward, so we also want to play with the collective performance, because at the end, if each agent is acting on its own, then at the end, where is the global solution taking advantage from? So we also try with the dual reward, and then we were also giving every agent a feedback signal every time an action was taken, but we also took into account the quality of the solution that was built at the end. We did some experiments, and then we took different groups of instances from the operation research library. There are instances with 10 jobs and 5 resources, 15 and 5, 20 and 5, and many more. And for each of them, we were just doing the experiments and taking into account the mean relative error per group. So here, compared to the previous reinforcement learning algorithm, we can see here that for each group, the algorithm was able to yield better results. And for the other table on the right, we were comparing with the ant colony optimization with the genetic algorithm, and also with the two-stage ant colony optimization. We can see that the algorithm is not outperforming all the others, but is able to find comparable results, and that's what we wanted from the first experiment. So try to find something that is able to find good results, and then by introducing a bit more the idea of having a more robust schedule, that's let's say the strong point of the approach. Besides this, we also did some experiments with the flexible job shop scheduling problem. So here, the idea of the instances is on top, but basically what we need to know here is that instead of knowing in which resource the operations need to be executed, we have alternatives. So here, what we know is that the first operation of job 1, for example, here, can either be executed on machine 1 for 10 time steps or machine 2 for 15 time steps. So for each operation, we have alternatives. Okay, so multiple machines can execute the operations, and the processing time will depend on the resource. That's the main idea in this kind of problem. According to the literature, we have two alternatives here. We can either solve it by using hierarchical or integrated approaches. Basically, the difference is you take into account both things at the same time. So you assign the machine and do the scheduling, or you do the routing first. So for each operation, you decide who is going to execute it, and then you have just a typical scheduling problem like the one I explained before. So here, let's say that we want to go for this kind of approach. So we will do the routing first and then the scheduling. And then we just decided that we will assign for each operation the fastest machine. Okay, what will happen then? So for each of them, I choose the one with the shortest processing time. And the best schedule I can get with that is one that will need 63 time units. Okay? If, on the other hand, instead of choosing the fastest machine here and processing job 1 operation 2 in machine 3 for 18 instead of doing it in machine 2 for 12, then we will see that we are able to come up with a schedule 10 time units. So we will be faster. So we will earn time on our side. So from here, we can see that having always the fastest machine, the one that looks like the fastest machine, to perform the operations is not always a good idea, because here you can see that machine 3, as it is a slow machine, never gets anything assigned. And then you are keeping machine 2 busy, and it actually needs to wait. So that's also something we wanted to avoid. Then what we did was to also run some experiments. And then in the first phase, we assign an agent per operation. So in order to take care of the routing, we took into account a dispatching rule that is called most work remaining, so MWKR. In this case, the agent will take into account, in order to select who is the machine who will execute me, I will take into account the amount of time that the different operations have already assigned. And then based on that, I will try to choose a machine that is not too busy and that it might finish my processing a bit earlier. And then in the second phase, once I know for all the machines who is going to execute what, then I already have an algorithm that can do that, and that's the one we explained in the first part. Then we ran some experiments. The original work on flexible job shop scheduling problem dates back to 1993, and these are the instances that were proposed. Some of the other algorithms were more recent, of course, and here we can see that except for the genetic algorithm, our algorithm was able to obtain better results compared to the taboo search and also the ant colony optimization and the evolutionary algorithm from the original proposal. So we were able to check that in this case, for the flexible job shop scenario, the algorithm was able to obtain comparable results or good results, and then we decided to check. We also check other scenarios, but it's not time to explain them all. Then we just decided to check, okay, now we are having results that in quality and in computational time, I mean, it doesn't take that long to get them. Let's see how we can deal with robustness, okay? So in real world applications, is something we know is that small uncertainty in the data can make the usual optimal solution completely meaningless from the application, the practical point of view. And then we wanted to check for the robust scheduling, how we can get a schedule that can be, I mean, we can be prepared for something that could happen. And then how can we measure robustness, or how we can incorporate it? So those were the main questions we had at the beginning. And then when searching in literature and in the different publications we found, we saw different ways in which we can do this. So to measure robustness, we can take into account the deviation from the original schedule. So when a user comes to you with a task to perform, you propose a schedule, and then if something happens, you will get something that is not what you propose. So the deviation from the original schedule is what is going to tell you how robust you are. You can also measure it by taking into account the stability or by measuring the number of changes that you require in order to fix the solution once something happens. Then, in order to check how we can incorporate or how we can prepare the schedule so they can be a bit more robust, here there are some approaches that are basically introducing what is called slack times. Here we can say one example could be, for example, the airlines. Once we book a flight, when you book it, you see that it can be, I don't know, for example, a short flight within Europe, 2 hours, 2 hours and a half, 2 hours, 45 minutes. For example, if you book it and it says 2:45, once you fly with the airline, once, twice, you will see that it never takes that time. So the actual flight takes less. But why is the airline then planning a bit more time? Because, of course, you need to take into account that boarding is not taking always the time you should. You should take into account the traffic, that airline traffic, also in the landing, or if, I don't know, maybe the plane has to arrive from somewhere else before you actually take it. So we can see that even airlines are doing this by introducing slack time. So what is basically the idea behind these techniques is to provide the tasks with extra execution time, that this extra execution time can be used to absorb some level of uncertainty. So you could use, going back to the manufacturing scenario, the knowledge you have about your resources in order to plan when do you think that these resources or the operations being scheduled in this resource will need extra execution time, because this is something that could be a machine that could break down at some point, for example. So you define your breakable resources, and then you protect, let's say, the operations that are scheduled on them. And then, for example, in the example to the left, you protect all the operations, and in the one to the right, you define that only your second resource is breakable, so you only protect the operations in the second one. Why am I making a difference? Because it's not the same to protect everything, because at the end, you are adding extra execution time. So if a user comes to you with tasks or an order, and you say it will take me 3 days for something that someone else will tell you I will need only 1 day, then you might lose a client. So you really have to be careful not to protect a lot, because then you might be saying that you will need more time than expected. So this is a typical solution for one of the instances of the operation research library. So here we have 6 machines and 6 jobs. And here we are showing the optimal solution. So it's showing 55 time units. But here we can see that in order to come up with the approach we propose, we were checking how critical the machines are. So for example, if we let's say that we are simulating, and we also did some experiments by incorporating some, let's say, unexpected events. So all the bars with yellow and red, these are all perturbations that can happen in the system. We just use specific distributions for that. And here we can see that on a random day, all the machines had a perturbation. So if you keep this idea into account, then you can see that if I use the temporal protection method that I was mentioning before, all the resources can be defined as breakable, and then you will end up protecting the operations in all of them. So our objective, if you protect all the operations here, then you will be telling the user, assuming this is days, that for the optimal solution you only needed 55 days, let's say, and if you protect everything, you will say that you will need 90 days. So our objective was to take into account in the original solution how critical are the machines. So here we can say that a machine breakdown on machine 2 or machine 6 will not have the same effect than on machine 4. Why is that? Because machine 2 and machine 6, they have too many operations scheduled one after the other, so too many consecutive operations. If something happens in between, for example, machine 6 at the very bottom, between operation 3 and 4, the purple and the green one, it won't have enough time. I mean, there is no idle time in between, so it can recover from the perturbation or the unexpected event. While on the other hand, for example, machine 4, it does have some idle time in between. So our objective was to define something that is called criticality, and then we allow the user, I mean the user or the expert that is using the tool, to identify the critical resources. So according to the problem you have, you can define when a resource is critical, once we start having too many operations scheduled one after the other. And then we decide the level of protection we want to give. Basically, you can add just a percentage of the processing time. So typically it can be 10, 15%, but of course, this is also that can also be learned by after executing several experiments. If we use this idea, then here we define that the machine is critical if it has 4 operations or more in a consecutive way. And then we were extending the processing time by 10%. And then here, then we will be telling the user we need 69 days instead of 90 as the original method. And that's a bit more realistic compared to the 55, which is the optimal solution. And we did some experiments by using different levels of perturbations, going from 1 to 6, less number of perturbations, and a higher number of perturbations. So we have, let's say, 6 levels of uncertainty by increasing the number of unexpected events. And then we can see in the y-axis here, the deviation in days. So if you use the original method, which is the blue one, then you will start having a higher deviation. Of course, you are protecting a lot. You are saying that it will take you longer than it actually is. But as the number of perturbations increase, of course, you start doing better. You deviate less because you already protected a lot. For the non-protected version, then you start somewhere in between, but you didn't protect, so you will start going up in the deviation as the number of unexpected events increase. And in our case, in the Greek one, we are able to more or less stay stable by taking into account these 2 constraints. So up to here, we were able to have, let's say, a specific approach that can take a scheduling problem plus some user specifications. It obtains near optimal solutions with different levels of robustness. It can identify the critical machines, and using this interface, user-friendly interface, the user can define all these parameters. Sorry. Then we were recently presented with this scenario where a 2-armed robot has to cooperate with a human operator in order to assemble light switches. These light switches can be either black or white. The sum by the people in charge of the control part, the working zone was divided in 4, so that the 2 arms of the robot won't collide. We have 2 workstations, right and left, and there are different constraints in assembly order. There are also constraints for tasks that have to be executed one after the other, so inseparable tasks. And since not all the components are available for the human operator, then of course collaboration is needed. So for this problem, we basically know how the robot will perform, the time it takes for the left arm, for the right arm, and for the human operator to execute each of the tasks. And this is quite similar to the flexible scenario I just explained. So we have 15 actions. They are all mentioned there. And having the set of tasks that we have to execute defined beforehand. For each of the tasks, we have the timing for the different, let's say, resources that we have in line. So the constraints, the ones in assembly order, and the constraints for the tasks that have to be executed one after the other, these are two different sets of constraints that we are receiving, and in order to translate it, this is just being taken into account in the action selection process. So basically, the input file, it changes with respect to the one we had before, and this is also something we had to adapt, but we were able to translate it, really, we can say with some modifications to the flexible job shop scenario. Then the part of assembling the different parts of the light switches can be seen as the operations to execute, the robot arm together with the operator. So we have 3 different resources or machines. They can differ in speed, and they will be our resources. And of course, the use of the zones and the precedence relationship are extra constraints. this is the proposed solution. So we have learning first. We have some sort of routing afterwards. So for each operation, we choose a machine. And in the phase 2, once we decided what will the robot do and what will the human operator do, we just have a sequencing problem in the same way that we have before. And we just executed this. The part of the mode optimization is something that's optional. It was not proposed by us. That's why I'm not explaining it. But if anyone is interested afterwards, it's similar to a local search. This is an optional step. I can explain it afterwards. So we were able to provide a solution. This was the requested format. It is anyway translated through our interface to something like this. And we were having results that we were able to compare to the previous solution they had at the company. They had the mixed integer linear programming first, where for 4 different types of files. So they were building light switches with a single button or 2 buttons. And that's the time in seconds that we'll need to actually execute it. And in this case, our algorithm was able to obtain better results. So for the 15 actions, the 4 zones, and having alternatives between 2 and 4 products with 1 or 2 buttons. That was the first scenario. For the kitting case, there are still things being done here. But the general idea is that full kits need to be delivered to a drop-off location. So if multiple automated guided vehicles are present, they can work in parallel to minimize the total time. So they have to move around by picking the components of the kits and then dropping them off in a specific location. Then they can take only up to 2 kits, and the specific locations in which they can move around, they have capacity constraints. So now we receive input file is an HTML file, so we have to adapt to this. We have components for the different kits, and that's how they are defined. And we have a load time to the AGV and unload time from the AGV. Of course, we have here the locations in the warehouse and the reachability table that is telling me from where I can move to where. So here, once having an input file, we calculate and store the distance matrix. And while there are still kits to deliver, then we assign the kits to the AGVs, following the previous idea. And then we are just moving to the kit storage by loading the times, using the processing time plus the loading time. And then we have to move to the product storage, load everything, and then go to the drop-off location. So there are still things being done here, but it's something we already, we think it's possible to solve it with the same scenario. The results for this so far is that the previous solution was using the PDDL, so the optic solver was able to obtain solutions for 1 AGV and 2 AGVs. We already have solutions for 6. And here, the algorithm is also able to obtain good results. We are also analyzing how to integrate, for the cases where it's needed, the idea of having a deep reinforcement learning for scheduling problems using this DQN approach. So as general remarks, we can say that it was possible to apply reinforcement learning for the different scenarios. The existing approach was modified to other scenarios, I mean, not the basic or the classic ones, but also to extend it to the light switches and the kitting case. The solutions obtained by the modified approach were able to improve the existing ones, and of course, we are evaluating or integrating deep RL for the applications for more complex scenarios. The different papers that were mentioned are listed here. Sorry for the coughing part.
So, thank you, Yailen, for the presentation. Now it's time for discussion. So, any questions from the audience? Question there?
Hi, thanks for the talk. That brings me back to a previous life in which I was doing research in meta-heuristics. So I have a general question. My intuition is that if you apply reinforcement learning and you get a solution, and you perturb that solution because, for example, in the real case, you have a machine that breaks or there are some other damages, starting from that solution and apply reinforcement learning should be faster and maybe provide better solution with respect to a meta-heuristic. So my question is, what do you think about that? And if you had experiences in trying to approach, to tackle this condition, this scenario? Thank you.
Yeah, thank you. Well, we also have the possibility to start not from scratch, I mean not learning from zero, but if you already have an experience by solving a specific problem, you can start with something that you already learned before. And if something is, I mean, we are also allowing the user to determine whether it wants to learn from scratch or to start from something that has been learned before, but we also allow the user to, to say whether he wants a protected schedule or not. So we can say, I can do this, I don't know, for example, in this scenario, you want to, I don't know, build 200 tables, I can finish this in 5 days. That's the optimal solution, but that's not the realistic one. So we could play something like this, and we can do it in 9 days, for example, if we go for the critical or criticality approach, so we are protecting a bit, or we can have a higher amount of, let's say, protection, and we can say that to be on the safe side, this can take, and you can change the amount of protection you can, let's say, you want to integrate. For the meta-heuristics, I didn't work a lot. I have worked with ant-colony optimization before, a bit with genetic algorithms. I guess something similar, it could be possible, but at the end, for example, if you go for the exact method, some of these constraints are a bit more hard to, let's say, to model or to integrate in the whole scenario. So it doesn't mean that with the other ones you couldn't do it, but as from this point of view where we are integrating pretty much all these constraints, then we think it's a bit more like generic approach that is more suitable to make some adaptations better than the other ones.
Other question? Okay.
Thank you very much for the presentation. I was wondering if a machine breaks down, is this algorithm somehow being able to do a rescheduling, taking this information into account? Or
right now, no.
You have to retrain it completely?
Well, in this version, not, but we did some experiments with that, but at the end, the papers we have are with this, that we just introduce some slack time, and then we are letting the machines or use this slack time in order to absorb the perturbation. So we just use the slack time to, like, it's just some part of the time that you had scheduled, and then it will take just this into account. So if the perturbation lasts 3 hours and you had only 1.5 as extra time, then everything will be delayed. But we did some experiments with also that alternative, and of course doing some rescheduling, but it's not the final version that we have, but it's also possible, of course, to reschedule.
I have a second question. In a factory, it's important to know where the bottlenecks are. If you want to buy a new machine, which machine should I buy? Is this algorithm also somehow showing or giving some sensitivity analysis where can I optimize?
You could indeed, if this idea of knowing what's the critical resource, I mean, if you have a machine that is really fast, then you will notice that you will use it more. And then by doing that, I mean, following that criteria is how we define the critical resources, but also the kind of operations that the machine can execute. So following this idea, of course, you can identify, and the more critical the machine is, of course, you will use it more. And if this is, of course, the kind of machine you will probably need to buy earlier than compared to the other ones. So the same idea could also be used, I would say.
Any other questions? Oh.
Thank you for your presentation, first of all, and just a question, I'm not an expert of this topic. Also for me, I started working on scheduling problem many, many years ago, but then I moved to other direction. So my impression is that adding a slack time is anyway adding a sort of cost, so the slack time per se is a cost. So I was, my impression that I mean, from the presentation, but as I said, I'm not absolutely expert of the topic, is that the selection of the select time is a bit done, let's say, not by hand, but on the basis of, let's say, reasonable considerations, done by some expert of the process. This is my impression at the moment. There is a way to optimize the choice of the select times, and also, I mean, not only the amount of the select time, but also the distribution over the machines which may require a select time. So there is a way to make this assignment of the select times a bit more, let's say, quantitative and optimizing in automatic way.
Yes, indeed, we could use another learning algorithm in order to learn how to do it. I mean, we didn't do it because it will make it a bit more complex, let's say, but indeed that's also something that could be, let's say, optimized or even learned. So you just play it and you let it run, and of course by using simulations or real data, if you do have it, then you can actually check whether you are integrating the slack times where it's needed, actually. Mm-hmm. And of course, yeah, that's also something we could deal with. At the end, we don't have real data anymore, so we were just, by generating these scenarios with just following some distributions, we were able to check these things. But indeed, it's also something, I mean, for now, we are just proposing something, then the user, of course, if you have experts in of the warehouse, then they will, of course, tell you, these are the machines where you will need it more, or this machine will need more, or even, we don't need it in the morning, the machine gets warm or heated in the afternoon, so just do it in the afternoon. So if you could use expert knowledge, but if not, then what we can do is also apply some learning there, and then, of course, learn this kind of things.
Okay. Thank you very much for the answer.
Other questions? Okay, so if there are no other questions, let's thank again Yailen for this presentation. And yeah, so we arrived to the end of the second seminar, and so just slight communication. Next week there won't be the Thursday seminar because we have the first big event of the BrIAS, so the conference on smart agriculture. So the seminars will be postponed of 1 week. So because Thursday and Friday of the next week we will have this conference on smart agriculture. So thanks for coming, and thanks again for the speakers, and see you in 2 weeks.